Good morning, everyone. We'll start. Today, we'll discuss another important technique for algorithm design called dynamic programming. All right. So this technique based on recurrences. The most important foundation of dynamic programming actually is the recurrence relations. So let's take a look at recurrence relation first. Then that will eventually will lead us to the technique of dynamic programming. So let's make a comparison between recurrence and the induction, mathematical induction. This is just two ways to look at the same thing. Recurrence typically look in this way, and mathematical induction goes this way. And inside the mathematical induction, actually, we will use recurrence. All right. So from n equal 1 to 2 to 3, and keep on going up. So here's n. Typically, that's what happens if we look at recurrence and mathematical induction. For example, if we look at the summation of first n odd numbers, a square of odd numbers, maybe I equal 1 to n. All right. So this one has a closed formula that is 3n, n over 3, 4n squared minus 1. That's a closed formula for this one. So if we try to use the mathematical induction to prove it, we'll go in this way. So we really go in this way to prove it. And if we look at the recurrence, so we can use sum. Let's erase this one. So call this sum Sn. All right. So then we can get a recurrence relation for this summation. So it's very easy to obtain in this case. All right. So based on the definition, we can easily obtain this. So this recurrence relation. We can compute the sum using this recurrence relation. So then if we use the recurrence relation this way, then computation will be done in top-down fashion. So we will extend this relation. So we can get n minus 2 plus 2n minus 1 plus 2n minus 3. All right. Now, if we try to use recurrence relation to compute the sum, I forgot square, sorry. Here the square, sorry. Forgot to put a square here. Otherwise, n squared. Okay, if not sum. Summation of first n in an odd number is n squared. All right. Now, if we try to use this recurrence relation to compute Sn in this way, so we can leave dirty work to computer. So this part, we really don't care how it's computed. So we can just call recursive function to use this relation. And computer will do the dirty job for us, extending summation to these things. It will be done by computer. All right. So if we use recurrence relation, just compute a function like this. Say declare function, compute this function by recursive calls. So if we compute Sn, so this function we just compute Sn minus 1 plus 2n minus 1 squared. So we do this. Then this part, the dirty work part, the tedious details will be carried out by computer. All right. Now, if we try to use mathematical induction to prove the formula, if we try to use mathematical induction to prove Sn really equals this one, actually in the middle, when we use mathematical induction, actually we implicitly use this recurrence relation. So you see the importance of recurrence relation. All right. But the way we look at these two things actually is from two different perspectives. For recurrence relation, typically we look things in this way. And for mathematical induction, we look things in this way. But they're actually the same thing. They're very closely related. All right. So then dynamic programming is really based on recurrence relation. We obtain the recurrence relation and try to use recurrence relation to compute a function efficiently. The keyword is computed efficiently. All right, we try to use the recurrence to compute a function or to solve a problem efficiently. So keyword is we really want to do it efficiently. If we don't care about efficiency, then it's quite simple. We can just do things like this. Just simply use recurrence relation, use a recurrence function or recursive procedure to compute it. All right, so let's take a look how we can use recursive relation or recursive relation to compute a function or to solve a problem. All right, so let's go back to our familiar example, Fibonacci number. So let's consider Fibonacci number. Oh, sorry, it's a color. Let me change the color. All right, so we have definition of Fibonacci number. We can easily compute this function by recursive call. We define recursive function. So it's really trivial, so we can easily do it in this way. So I write it as a function, as a recursive function. All right, so Fn right? So of course, there are boundary condition F0 equal 1, F0 F1 equals 1. We need to do this. All right. The key part is really this recursive function, recursive call. So it's really very, very simple to implement this one. But the problem is the efficiency. How fast does this one run? The speed, the running time of this one. If we care about efficiency, if you try to implement computation of Fibonacci number in this way, you will wait forever if you want to compute F100. You will never get an answer. So I will explain the reason why it will not really give us answer, because the algorithm or the function is clearly, obviously correct. It's so easy, so simple. But problem is really running time, the efficiency. All right. Now, so let's take a look at running time of this one. So suppose we use T of n. So that's a time to compute f of n. So then from this recurrence function, we can see Tn obey this recurrence relation, the time it takes, plus time for addition, because length is proportional to f of n. So basically it's proportional to n. So here will be order of n. That's the recurrence we get. Unfortunately, the solution for this one is very bad. So roughly, instead of big, maybe I change it to big O because it's maybe not very tight. So let me write big O instead of theta. Okay. That's the running time of this simple recursive function. It's exponential. So it's grow very, very fast with n. Therefore, for n equal 100, you will never get an answer if you implement it in this way. Now you may wonder why is this simple computation will take that much time. So we try to understand the reason and then try to find a solution to overcome this problem, all right, or this obstacle. So why this one takes this much time? It's why it's so slow. So the reason is because of overlapping problems or overlapping subproblems that cause Instead of problem, maybe call it instances, sub-instances. Because overlapping, a lot of overlapping sub-problem or sub-instances in extending the recurrence in the computation using this recurrence function. So let's see what happens. All right. So let's consider computation of say F10, F9 maybe. Okay, 9 is good enough. All right. So let's look at the recursion tree to see how this one is computed. All right, in order to compute F9, what happens is we use the algorithm, so recursive function, so we need to compute F8 and F7. All right, so there are recursive call for F8 and F7. So independently, F8 will do F7 and F6. And F7 will require us to compute F6 and F5. So you see what happens? Overlapping sub-instances. When we do F8, we require to compute F6. When we want to compute F7, we also want to compute F6, and they will be computed independently. We compute F6 twice. All right, so if you extend further, we'll see it's getting even worse. Same problem, sub-instance occur many, many times. All right, so if we look at F4, or F5 maybe, okay, so F5, one here, F5, one here, F5, one here, F5, one here. So the reason it's so slow is because we compute F5 so many times. So we repeatedly computing F5. That really slows down because there's repetition of computation. All right. Now, how can we overcome this difficulty? The dynamic program is a way to avoid the repetition of computation when we're computing a recursive relation. So of course, for Fibonacci number, it's very, very simple. Instead of doing the recurrence relation this way, what we do, of course, we'll use an array to compute it. So for I equal 1 to n, do fn, fn minus 1 plus fn minus 2. That's what we do, right? So what's the difference between this one and the previous one? They look almost identical, right? Except that I use small f and big F, but they're same thing, right? It's not matter. I can change the big F to small f. So if we make a comparison. So these two, they're same thing, right? What's the difference? F, this F and this F, they're just symbols, they're not really matter. The difference is here F is an array, right? Here F is an array. 1 to n. Here small f, it's a function. So what's the difference between this function and array? The difference is here, the value of the two fn minus 1 and fn minus 2 are computed already. So when we want to compute fn, these two values are known. Values of these two computed already. So instead of here, when we want to compute Fn, actually the value of Fn minus 1 and Fn minus 1 are computed online. So we don't know their value. We need to compute it. So in order to get these value, we use same recurrence relation and keep on doing it. So that's the key difference, the fundamental difference. Here the value are known. When we want to use these two values, the value are known already. But here are different. When we want to use these two values, we compute their value online. Say, compute their value online. So that's the difference between the recursive implementation of computing Fibonacci number and the array implementation. The time here is, as I mentioned, the time for this one is roughly and time here is n squared. So that's a huge difference from exponential time to polynomial time. Here it's not order of n, because the length of number is still n digits. So addition is not constant time, rather it's n squared for the whole process. Addition is order of n time. All right. Okay. So that illustrates the idea of dynamic programming. Actually, this one qualifies. You can say this one is an example of dynamic programming. It's a very, very simple example. All right. Okay. So let me give you one more example to illustrate this idea, the idea behind this. All right. So consider the computation of the well-known number n choose n. Computation of this. It's tedious, right? By definition, if I want you to compute, say, 10 choose 5, you can write the formula in this way. Okay, so you can do it in this. It's looks very tedious if we do things like this. Without a calculator, I think you really don't want to compute things like this. It's too difficult, right? It's too easy to make a mistake because there are many multiplications. All right, so perhaps we use recurrence relation. So there are recurrence relation for this one, of course. N choose m for m, n choose m, m choose n equal n minus 1 choose n plus m minus 1 choose n minus 1. So perhaps it's better to use recurrence relation because here I only need to deal with addition instead of multiplication many times. So certainly this one looks to be quite appealing because I only need addition. I don't care what happened, how to compare these two things. I just recursively do it, eventually deal with addition, right? But if you use this recurrence relation to compare this, we'll fall into the same trap again because of overlapping of sub-instances or overlapping of sub-problems. So for example, to compute 10, say 5, all right, if we extend it, then we need to compute 9 choose 5 or 9 choose 4. All right, now if we extend again here 8, 5, 8, 4. So here we'll see that 8, 4 need to be computed twice. We have overlapping here. Same problem occurs. All right. Of course, we know that for this one, it's easy. We don't compute it in this way. Typically, we compute it in this way, so-called the Yang-Hui triangle. In the Western world, it's known as the Pascal triangle, but actually Yang-Hui published this much, much earlier. So it's originally actually obtained. Original author is Jiang Xi. Yang Xi was the first one to publish it, but actually the work is not done by him. All right. So anyway, we all know how to do it in a very simple way instead of using this. So let's see. So we start with simple ones. Now, in order to compute this one, compute the number here, it's just addition of these two. So we'll simply just add them up to 1. Okay, so next row, then 1 addition of these two give us 3, addition of these two give us 3. So this one is 1. Okay, so let me just draw it in this way, how it's computed. All right. So you see, it's so easy. Oh, sorry. All right. Now, again, this illustrates our idea of dynamic programming. When we want to compute this number 6, all right, so the required two numbers, these two are known already. Okay, so here the 4 choose 2. Okay. When we want to compute the 4 choose 2, 3 choose 2 and 3 choose 1. These two numbers are known already. All right. So again, next row, these numbers. Again, it's very easy. 5, 10, 5. Sorry, 10, 5, 5. Okay. So let me erase this. So again, that's illustrates our dynamic programming. In order to compute recurrence as M10, we do it in this way. Maybe it's a drawing. Actually, in the drawing, maybe if it reverses and it's called bottom up. But here it looks like top down. But actually, it's just a way of drawing. It's bottom up fashion. We compute small value first, then larger value. The key point is when we want to compute the value required to compute this one are known already. So when we want to compute this one, these two values are computed already. All right, so you get the basic idea? So dynamic programming is really based on recurrence. In order to compute the recurrence efficiently, we need to avoid the difficulty caused or the inefficiency caused by overlapping sub-instances. So dynamic programming allows us to avoid the repetition of computation by computing recurrence in a bottom-up fashion. Bottom-up fashion, bottom-up does not mean this drawing. It's referred to the value. Okay, later on I will make it more explicit what we mean by bottom-up. The key point is when we want to compute the value required to compute this value are computed already. That's the meaning of bottom-up. All right. Now let's make a comparison between dynamic programming and divide and conquer. Divide and conquer is also a method based on recurrence. All right, for example, merge sort. The merge sort algorithm. Okay, so let's see. All right, so in order to do that, divide and conquer is also based on recurrence relation. So to solve this problem, we evenly divide these 8 numbers into 2 groups. Then use same method. Say, use merge sort for this part and use merge sort for this part. So to produce 2 sorted lists, so S1 and S2. Then merge S1 and S2. All right. So here again, it's based on recurrence relation. So merge sort recurrence relation is the following. It's roughly said. I just illustrate the idea. Okay. So merge sort of S equal merge it's not precise. All right. So merge sort of S1 and merge sort of S2. So illustrate the idea. So that's a recurrence relation. But why in this case, we can just use this recurrence in a top-down manner. We just use a recursive procedure to compute it. And all dirty work are done by computer. We don't care. Just use this relation, write a recursive procedure. Why this one works? It's very efficient. Give us n log n time algorithm. It's very efficient. So why the previous example, the Fibonacci number, it's much easier than this one actually. But over there, it does not work. The reason is here we don't have overlapping. Yeah, exactly. No overlapping at all here. The sorting of these two parts are independent of each other, so they can be solved independently. So there are no overlapping when we try to solve these two sub-problems. So therefore, it's very efficient. All right. The main problem for solving recurrence is sometimes there are overlappings. Later on, I will maybe on Thursday. It's more subtle than we just explained. Just overlapping or no overlapping. It's more than that actually. Okay, but here if we make a comparison, we can see for Fibonacci numbers there are a lot of overlapping. For binomial coefficients, there are a lot of overlappings if we use top-down approach. But for merge sorts, there are no overlapping. All right. Okay, so the main idea of dynamic programming is try to avoid overlapping by computing a recurrence relation in a bottom-up fashion. So let me summarize the idea of dynamic programming, then just give you actual examples. Of course, you have seen two examples already, the computation of Fibonacci number and computation of binomial coefficients, okay? But these two are very, very simple examples, all right? So again, as I explained, the key idea is recurrence. So that's these two steps actually allow us to define the recurrence relation. We find the recurrence relation, all right? Then as far as efficiency concerned, then we solve the problem in a bottom-up fashion. So bottom-up manner means so small mean typically it's small. Maybe no need to quote it. Typically it is small. All right, so that's the key idea involved in dynamic programming. So this step is really dealing with efficiency. So in order to make algorithm run as fast as possible, so the final step, so the key step, the real step in computing recurrence, the bottom-up manner is very important. All right, so let's give you a big picture of how we use dynamic programming to solve a problem. All right, so now I'll give you some concrete example to see how we apply this idea to solve problems. Okay, so let's start with shortest path in a DAG, a familiar problem. But actually it plays a very, very important role in dynamic programming. All right, we all know how to solve this problem in a DAG, right? Quite simple. Use Bellman font, one scan from left to right. Okay, make a comparison with dynamic programming, how we solve this problem. All right, so we have a DAG. So since it's a DAG, its vertices can be ordered linearly so that all edges goes from left to right. All edges goes from left to right. That's the beauty about the DAG. It has this very nice property. We can order edges in this way. All the vertices from left to right. So all edges goes from left to right. Okay. So that's a DAG. All right. So suppose that's starting vertex. So S is here. This S. So shortest path problem, we want to find the shortest path from S to all other vertices. Okay, so some edge weight can be negative. So let's put some weight on. Let me draw one more maybe. So maybe this 1, that's 3, that's -3, maybe 2, -4, 3, -1 maybe. Okay, here 2, here maybe also -1 maybe. Okay, so suppose we have this DAG and we want to compute short path from S to all other vertices. Okay, so let's consider distance first. Let's ignore the shortest path. Let's compute the value first. Later on, we'll come back to actual path. So let's compute distance instead of path. Okay, so these two are very closely related. So we compute the distance, d s v for every vertex. That's what we're going to compute. Distance, okay, not actual path. Later on, I come back to shortest path. How we use distance, we can find the shortest path. So let's focus on distance, how we compute distance. Of course, Bellman font. We know how to do it. Use Bellman font. Use one scan from left to right. Relax all edges going out from all vertices from left to right. So first vertex, we consider relax these two edges first. So update these two edges. All right. Then go to next vertex, update these 3 edges, and so on. That's how the Bellman font algorithm works. Okay. Now we use dynamic programming to solve this problem. So how do we do it? So here, what we are going to do is sub-problems. Of course, in order to reach this vertex, so we want to compute distance from S to this vertex V. What sub-instance for this one? We need to compute distance from S to these 2 vertices. Let's see. So these 2. So these 2 are sub-instances. In order to solve this sub-instance, we need to solve these 2 sub-instances. All right. So we have a collection of sub-instances. Actually, each vertex can be regarded as a sub-instance. So each vertex, if I fix the vertex, then this one is a sub-instance. A problem we need to solve. So what we are going to do is get a relation, recurrence relation for this value. All right. So which is very easy to obtain. Okay. So we obtain a recurrence relation for this value. Okay, let's see. Okay. So 0, 1 here. I forgot to wait. Does not matter. Okay, put it 3. Maybe. Okay, so we get the recurrence relation for this number. So what's the recurrence relation for this number? Say let's add vertices as V1, say V2, and Vn. All right. So distance from S to Vi. This is distance from S to Vj. So Vj is the neighbor, right? So plus the weight of edge, Vj, Vi. Okay, now Vj, Vi is an edge. Vj, Vi is an edge. So this one we take a minimum. That's a recurrence relation for computing the distance from S to vertex Vi. It's very simple, very easy to obtain, right? So what we have is this vertex Vi, color. This vertex Vi. So for each in neighbor of Vi, any path can go through any of these vertices. So if there are 3 in neighbors, so each path, shortest path, may go through these 3 vertices. So it can go through this vertex, or may go through this vertex, or may go through this vertex. We don't know which one. So it will be minimum of them. So that's the recurrence relation. Take the minimum of them. All right? So we get a recurrence relation. Now it's easy to see that if we compute this recurrence relation, just by use this recurrence relation using top-down approach, we'll see a lot of overlapping problems. Right? Because some vertex, the distance from S to that vertex will be required several times. It's very easy to see it. Okay, so for example, this one, to compute the distance to this vertex, we require computational distance from these 2, right? Now, we may have this one. Now, when we want to compute distance for this vertex, it will require to compute distance of this one and this one. So you see the repetition. Make a comparison with the computation of Fibonacci number. So let's see. Let's take a look at dependency of how we compute Fibonacci number. All right. So we can draw a graph. It's a dependence graph to see how these values are related, are used in order to compute F2. We need F1 and F0. When we want to compute F3, we need F2 and F1. When we want to compute F4, we need F2 and F3. What do we see? We see a diagram. In this case, it's a DAG. So the method we're using array to compute it, actually we do things in this manner. Scan from left to right in this DAG. Therefore, we avoid repetition of computation. All right. So here for the distance computation, same thing. So how do we compute this recurrence efficiently to avoid the inefficiency caused by overlapping? What we can do is compute distance in this manner. That's called bottom up. Okay, bottom up does not mean you have to physically go from bottom to top. It can go from left to right to left. It meaning compute smaller instances first. All right. So what we do is starting with the starting vertex, compute distance from S to this vertex, first vertex to V2, compute this one first. So that's of course give us 1. Then compute distance to V3 to this vertex. All right, so this give us -2. So it's between this path and this path, right? So that's give us -2. Okay. Then we compute distance from S to V3. So in this case, it's only one edge. Maybe I draw another edge. Okay. -3. So there will be 2 paths. Either we do this way, or we go this way. Okay. So just use this recurrence relation. It will give us correct value. It will be -3. Okay. So we compute distance -3, and so on. That's how dynamic program works in this case. Make a comparison with Bellman-Ford. Bellman-Ford consider edges for each vertex. For each vertex, consider edges going out. Bellman-Ford. So, for example, starting from this vertex, it considers these edges going out. All right. So dynamic programming actually considers all edges coming into a vertex. So when we compute, let's see. When we compute the distance from S to this vertex, V3, we consider all edges coming into this vertex. So there's a difference between Bellman-Ford and dynamic programming. Actually, they're the same thing. If you reverse the order, if we look from right to left, if you look from right to left, so Bellman-Ford from right to left, actually it's dynamic programming from left to right. All right. Actually, they're really the same thing, but just from 2 different angles. So what we have seen here is we compute distance in a bottom-up fashion that will allow us to avoid recomputation for overlapping subproblems. So this shortest path problem in a DAG is a typical example of dynamic programming. So what happens is we have a recurrence relation here. So that's recurrence. And then we compute it in a bottom-up fashion. So that's how we compute it in a bottom-up fashion. So that's bottom-up fashion. Okay. So really, dynamic programming is based on 2 things, recurrence and bottom-up fashion. Combining these 2 together, we'll be able to solve a problem efficiently. And this one is a key example of dynamic programming. Actually, every dynamic programming it just looks like shortest path in a DAG. So the actual DAG may be complicated, maybe not obvious, but actually every dynamic program there is underlying structure that is a DAG. All right, I will elaborate on this after we come back after the break. So let me make the statement first. So which is very important. All right, so let's have a break. After break, I will elaborate this and discuss more examples. So this is a very simple example. Later on, we'll see complicated examples. Actually, it's not easy to use to obtain a dynamic programming algorithm because to obtain recurrences, find the correct subproblem, sub-instances are not trivial. Yeah, yes, good question. The proof. Do we need to prove it? How do we prove it? Actually, the correctness of dynamic programming is quite easy to prove because the key thing is recurrence. What do we need is to prove that recurrence is correct. Once that's when it's done, it's obvious. All right, but it's a very good question. How about the correctness? How do we prove it? The proof part is really mathematical. It's discrete math. Why recurrence is correct. So the key part is correctness of recurrence. All right, so let's take a break.